Good morning. Welcome to the seminar on control systems. It is a seminar and a webinar. We have seen some introductory concepts about control systems and the numerical analysis concept with the control systems. However, the requirement of numerical analysis and the numerical computations in control systems is vast, and the control system cannot bypass the numerical analysis and computations. We saw some of the key concepts, mathematical concepts associated with control system numerical methods and computational analysis. Some of them like Laplace transform, curve fitting, then Nyquist plot, board analysis, etc. But now we are going to see some of the new concepts which are going to aid the control system behavior and the system analysis in terms of simple concepts. I have worked out some of the equations related to understanding of the transforms, complex analysis, integral and differential equations, etc. We have the integral and differential equations. We know that derivatives or differential equations are a mathematical solution to analyzing a particular part of a signal or part of a diagram or part of a geometry, wherein the linear equations are just a simple equations wherein they get a value and it is just a curve or a straight line which can be obtained from the linear equation method of solving the values of x and y. But in the differential equations it is not like that. It is different from linear equations wherein the differential equations are going to analyze the part of a surface, part of an area in mechanical systems, and part of a particular curve or enclosed area in a particular plot of the control system's output, or even in electronic design, they are going to be extensively used for analyzing the part of a signal. The signal incoming may be a sinusoidal or cosine, or even maybe a ramp or some other signal, but it has to be analyzed quite well so that we obtain the nature of the signal in a very apt manner, such that we partially analyze the signal part by part, and then it is easy for us to eliminate particular noise in the signal, or you can also integrate the parts of the signal as a whole to understand the signal better. The part 1 of the signal, which is going to be less in amplitude value than the part 2 of the signal, and part 2 of the signal can be less in amplitude than the part 3 of the signal. This is obtained by the derivatives. And it is very difficult to analyze such a derivative at the first sight, but when we work out some derivative or differential equation, we can get the values such that we can compare the amplitudes of the values. Then we can understand that this particular curve is a rising curve, this particular curve will be rising for a particular period, time period, and then it will be falling in value. This I have worked out to show a simple example of the differential equation and the need for integral. We are taking a square. Here seen is a square box. This is a square. It has got equal sides. Then we want to constrain this square into a particular rectangle. In this case, what happens? The sides of the square are not going to be the same, but the area of the square should not vary. So I am going to contain this area of the square into a rectangle. In this case, the x also varies and y also varies. So x is going to vary relatively with respect to y, or y is going to vary relatively with respect to x. Here both the terms are varying. We cannot avoid both the terms. Then if I want to consider a very small rectangle, here also you have the rectangle dimensions obtained by constraining this particular length and breadth of the square. Here the length becomes larger and the breadth becomes very smaller. However, the variation of x and y are simultaneous. The variation of x cannot be restricted, or variation of y cannot be restricted. Whereas on the right side you can see a particular rectangle carved out of a square. Here the variation of y is obvious, but variation of x is not there. I am taking the same x of the square and I am plotting the x of the next rectangle. Then the top rectangle is the variation of again y, there is no variation of x. This means variation of x with respect to y is not there, but variation of y is independent of variation of x. This is called as a partial equation. We obtain a partial equation and then we take the solution for the partial differential equations in this manner. This is obtained by having one set of variable as constant and considering another variable as a variant in a particular differential equation. This is called as a partial fraction or partial equation, differential equation method. It is a partial differential equation method. There is another method called as a partial fraction for splitting the values of numerator of the polynomial, which we are also going to see later. However, we want to see the corresponding equation for this particular partial differential equation. We can see that the x was constant and y was variant. Here, if we want to write the equation of the particular square box, then I can write it as f of x comma y. Here you can see f of x comma y equals f of y plus x comma y plus del y minus f of xy divided by del y. So we have seen that this particular variant here is y, and with respect to the y variation, what happens to this function? When we analyze this particular function, f of x comma y plus del y minus f of xy, we are going to eliminate one set of rectangle. Seemingly this particular rectangle is going to be one eliminated, and we are going to analyze this particular rectangle with this equation. So this is called as a partial differential equation, which can convert a geometry into a very good equation for analysis. So there is no need of analyzing geometry by inputting all the values one by one. Rather, we can use the partial differential equation easily. We have the two rectangles constructed. Here this is the origin 0. The 0 to y1 is one rectangle, and this is the y max. So y max minus y1 is another rectangle. So we can say that this particular rectangle starts from y1 and then it ends in y max minus y1 with reference to the lower rectangle, which has to be omitted while analyzing the partial differential equations. This is one example comparing a geometry with the partial differential equation, but it is not exactly matching what you may think in mind regarding the partial differential equation. So seeing the symbols dou and del, all these symbols which may confuse. Having seen this partial differential equation, we want to characterize the Laplace transform. Laplace transform is a method which is going to take these functions, whether it is a differential equation, whether it is a derivative or an integral or an exponential curve or a sine curve or a cosine curve. It is going to take these particular time variants and then going to convert it into a S-domain. S-domain is very easy for analyzing these particular functions in terms of algebra. We don't have any other alternative of considering the functions time varying to be analyzed as algebra or arithmetics. This is the only way, the S-domain, wherein it can produce simple mathematical calculations instead of complex ones. Hence, we have the Laplace transform of a particular function defined in terms of the following. Here shown is the simple integral function. Just now we spoke about differential and integrals. As I said, the particular derivatives which are obtained from dividing the particular area into parts and then integrating the derivatives all together into a single unit is being done for analyzing the particular area formed by a signal or a geometry or etc. However, shown is just a simple equation, integral equation. This integral equation varies from 0 to t f of tau t d tau. That means this d tau is a differential derivative, or it can be said that it is the difference of time. This is a function which varies with time, and there is a limit for the function 0 to t. T is the maximum limit. This same function as an integral can be split into two functions. That is, one is from 0 to t, another is from t to t1. So in this case, we can remember the example of the rectangular boxes made from square. One is taken from 0 to y1, another is taken from y1 to y max. Similarly, this particular integral is split into time, that is the x-axis, in this manner. If I want to put Laplace transform for this particular function, then it comes to a simple 1 by s f of s. The Laplace transform of this particular function is f of s by s, that is equal to 1 by s f of s. This means that Laplace transform transfers this particular integral equation into just a ratio that can be easily manipulated for a particular value of s. Why this is done? This is done for simple algebra that can be derived out of equations. We don't want to analyze equations value by value in the time domain. If we analyze the equation value by value, it is like a graphical plot. We don't want to always rely on graphical plot, time consuming 2 hours or 3 hours for constructing a sine signal. If you put y equal to sine x, then if you give x values starting from 0, then increasing the step size by 0.2, 0, 0.2, 0.4, 0.6, 0.8, like that. If we construct, then it will take hours to plot this particular sine wave in a graph, and it will not be a continuous one, it will be a discrete one. We have to connect all the discrete points to form a full sine wave. And this we do not want in analyzing the signal for the control systems. Rather, we want to analyze the control system behavior as well as the control system signals which are input to the system. Hence, we have the Laplace transform. I want to show you an example of the Laplace transform which has got two exponential additions. One is the exponential curve, that is e power minus t, and another is e power minus 2t. These two curves form a particular exponential curve, but shown is the accumulation or the sum of two terms, exponential terms, e power minus t and e power minus 2t. However, you can see below the graph of rising exponential, which is shown here, and one is decaying exponential shown here. So if we have got e power minus t, then it is a decaying exponential. If we have got e power t, it is a rising exponential. I think that it is a rising exponential, and we have, if this is a rising exponential, e power t and e power 2t, then we have two rising exponential curves. The difference between the values at the same time instant between the two curves will be this value and this value. This will lead to a midpoint from which a signal is constructed. This is how a particular rising exponential curve, addition or subtraction, leads to a particular point in the xy plane, which is going to give rise to a complex signal. This is how signals are being constructed in a control system generator. However, the control system processes these signals. Control system has got a generator, it has got a processor, and it has got a filter, and it has got an output section. These are the four sections of the control system. And moreover, the control system, how it is going to process the signal depends on whether it has got a feedback or a non-feedback system. Now we have seen the example of an exponential system, but this is going to be transformed into S domain, the Laplace transform. So we have got e power minus 2t. We have got e power minus 2t, and we have got e power t, then if we have got e power minus t, then it is transformed into 1 by s plus 1. Then e power minus 2t is transformed into 1 by s plus 2. We have the intermediate symbol minus, which is a negation, which we are bringing it down. So this particular exponential function of time domain or time variant is being transformed into a s domain 1 by s plus 1 minus 1 by s plus 2, which is looking like an algebra that can be used for manipulation of these particular exponential time variants in terms of Laplace transform. Hence, Laplace transform has got lot of transformations of converting the time domain signal, namely step response, unit response, cosine function, sine function, damped sine, etc., impulse function. All these functions are time response functions, but these can be converted into a S domain wherein easily they can be algebraically manipulated. And the Laplace transform is extensively used in the control systems for extensive analysis and to determine how the control system is going to behave with the input signals. We want to start with the Laplace transform introduction, and we will continue later with some in-depth analysis of other partial fractions or Laplace transformations, which are going to work out on the partially obtained fractions and then the easy manipulation of such systems with numerical computation and analysis. Thank you very much for listening.